Hello, I'm Bjarne Stroustrup. I'd like to tell a bit about C++, why the language looks like it does, and present some of the main techniques that the language was designed to support. The talk has three main parts. First, I'll talk a bit about the origins of C++, the problems it was originally designed to solve, and the aims I had for the design, and present some of the rules that developed for the design of the language. Next, I'll present the key techniques, programming techniques that the language supports, and the language features that are there to support that kind of programming. That means things like classes, abstract classes, derived classes, uses of class hierarchies, templates, and runtime type identification. And finally, I will present some features specifically designed to support the writing of larger programs, namely namespaces and exception handling. Towards the end, I will look a little bit about how C++ is currently used and how it might be used in the future. My main sort of idea about languages is that a language is someone's response to a set of problems at a given time. That is, a language is there to solve problems rather than being an interesting item in its own right. Our problems and our understanding of those problems naturally change over time, and as long as a language is a good solution to problems that are faced by real programmers in real code, the language will live, and the language will grow to meet the needs of the programmers. The origins of C++ goes back a long way. One of the direct courses of C++ was a project I worked on at the University of Cambridge in England, where I was working for my PhD. I was studying distributed systems and the distribution of software running on such systems. I built a simulator to give me data about such systems. This simulator was written in Simula, was for the time at least rather a complicated program. I had encountered Simula before, but I was very pleasantly surprised when I used Simula there. Not only did it allow me to write my program, it also helped me think about the design of the program, the class concept of Simula, the way you could build upon classes, the coroutine mechanism of Simula, all helped me organize my thoughts. Secondarily, debugging that program was rather pleasant. The strong type checking helped me a lot, and made sure that I didn't violate my own rules as I had built them into the program in form of classes. Actually, the amount of help I got from the strong type system was somewhat of a surprise to me, because I had previously encountered Pascal and found its strong type checking rather counterproductive. It always seemed to me that the type checking checked some implementation directed set of rules that got in the way of my programs. The difference between Simula and Pascal was that the rules checked by Simula, by and large, was the rules for the user-defined types I had defined, the classes. And when the strong type checking found something, it tended to be a violation of my own rules, and I couldn't object too much to that. So I got the program written, got it debugged, it ran pretty nicely. Unfortunately, I ran into one major snag. The runtime of that program for real runs as opposed to debugging runs were rather extraordinary, and I was soaking up my department's computing budget rather fast on our mainframe. So I had to find a way of getting this program to run more efficiently, or I would have to leave Cambridge without a PhD. Now, there are a couple of classical solutions to this problem, like I could get my own computer, but that wasn't quite feasible because a computer like that cost several million pounds, and I certainly didn't have that kind of money. Alternatively, I could wait for hardware to get cheaper, but that would have taken at least 8 years or so. I could try and get Simula to run more efficiently, but I had the greatest respect for the people who had designed and implemented Simula, and I knew they were probably better at that job than I was. And anyway, my job was not to invent languages or implement Simula, it was to study distributed computing. So in the end, I decided to rewrite my simulator in BCPL and run it on a research machine that was so poorly supported that the chemists and the astrophysicists that soak up the main machines couldn't use it. BCPL is a direct ancestor of the C language and is a language that makes C look like a very high-level language. Getting my simulator rewritten into BCPL and running on a research machine was rather painful. Debugging it was hard. As a matter of fact, I lost sort of half of my hair in the process of debugging that program. But there was some real advantages. The simulator ran fast, very fast, so I could get my data. And the problems with BCPL was all overcome. They were not major. There's no coroutines in BCPL, so we added them, things like that. This led me to some ideas of what was important for a tool for work in systems programming in general. I wanted a tool that provided the support for program organization that Simula provided, the help to thinking, the help to design that Simula provided. On the other hand, I wanted something that ran really fast when it had to, like BCPL or C. I wanted something that was easy to port, something that required not very much support from the environment, and preferably something that was available. These ideas later came in handy when I found myself involved in studying some things at Bell Labs a little bit later. There I developed a language which was initially called C with classes, which was meant to deliver the help for design and thinking and program organization from Simula, but with the efficiency and flexibility of C. There's two questions that are often asked about C with classes and later with C++. The first is why C, and the other one is why the Simula-like classes. I chose C primarily because it was the best systems programming language available. C is flexible. You can do anything you like with it. It's efficient if you know how to use it, and it's portable in a reasonable way. It's available on most machines and quite importantly, it's known to most people in this area. If you want to build a new language, a new system, it's quite useful not to have to reinvent every wheel. So I took the attitude that computation as such was a problem solved by Dennis Ritchie in the design of C, and my business was program organization. Clearly, C is not the most beautiful language ever. There's a lot of flaws, but they're second-order flaws. I consider the C declarative syntax an experiment that failed, but it's not critical. I've never met any halfway competent programmer that couldn't master what they needed to master about the C syntax in a couple of days or a couple of weeks. The only thing that really bothered me and had something to do with the way you write programs was the weak type system of C, and I therefore proceeded to improve the static type checking in C. So C++ is strongly typed. Classes came in as the primary mean of program organization. The idea being that you organize your programs by looking at the application area. You look for the fundamental concepts in an application area and you try to map them into the program in the form of classes, that is user-defined types. And you use the static type checking to check that you have used the user-defined types according to the rules that you can derive from what fits with the concept. I note that reuse was not a primary aim of mine. There's a lot of talk about object-oriented programming and reuse. And reuse is something you get if you have a set of well-worked-out concepts well represented in your program. Then you can reuse those classes or those collections of classes. It's not something that comes magically from language features. It's something that comes from thinking clearly about issues, getting useful concepts isolated and represented clearly. I developed C with classes and later C++ in the Computer Science Research Center at Bell Labs in Murray Hill. That's in New Jersey in the United States. And I think my work environment there was of great importance in the sense that a language will reflect the environment in which it is created and the kind of uses that it's put to. In that sense, a language is like any other big system. The work in those days were a bit of everything. Lots of different kind of works done in the labs. And my main job was not to design programming languages, it was to get some work done. My work had a lot to do with simulations of things to do with distributed systems. So a lot of the input to the design of C with classes and later C++ came from people dealing with systems programming, dealing with distributed systems, dealing with design of networks, dealing with layouts of VLSI and boards, things like that. There was a lot of emphasis on doing things that was useful to colleagues in general, useful to other people around. On the other hand, there was a freedom for deadlines. Nobody was telling me when I had to deliver the next release. And very importantly, there was a freedom from fads and commercialism. I didn't have to produce something that could sell, that fitted nicely on glossy brochures, and I didn't have to produce something that would please academic reviewers keen on the latest intellectual fads. I could focus directly on the programmers writing production code, not on advertising managers or sort of the guardians of academic fashion. C with classes was a medium success, and that that turned out to be a problem. A medium success is something that is clearly a help to a lot of people, but not enough help to pay for an infrastructure. In other words, somebody who produces a medium design will end up supporting it forever. So I was the support and development organization for C with classes, and I would keep on being that for a long time. Since I wasn't too keen on doing maintenance and hotline support for the rest of my life, I was looking for a way of getting out of the dilemma. And there seemed to me to be exactly two ways out of the dilemma. I could either improve the language so that it could provide more benefits to the users, allow people to write code better, make greater changes to their organizations. That would make the language more popular, would get more users, and that would allow to pay for the infrastructure that it needed, supports, development, teaching, compilers, porting, that kind of stuff. And the alternative was, of course, to stop supporting C with classes, and then the users would go away, and that would solve the problem. On the other hand, the users were my friends, and just dropping them that didn't seem to be fair at all. I later learned that there actually was a third alternative, but I'm somewhat pleased that I didn't think of it at the time, because the third alternative, which is sort of a conventional solution, is simply to add hype, more advertising, more glosses, talk people into using it. But fortunately, I didn't think about that at all. When I designed C with classes, some criteria for what was useful developed. Actually, the origin of that goes back to my work with Simula and BCPL, and over the years it grew into a set of rules of thumb. You could call them principles, but that sounds so pretentious, so I'll stick with rules of thumb. First of all, C++ is a language. It's not a complete system, in that it differs from people trying to provide a complete environment for programming and use, like it is common in the Lisp or Smalltalk world. On the other hand, it has the effect that if you work in C++ on a Unix system, C++ will feel like a Unix language. It will have the user interface that you have on your Unix system. It'll have the libraries you're used to. It'll have the feel of Unix. If, on the other hand, you work under DOS, it'll feel like a DOS language. And presumably you like the system you're working on, so that's fine. It also simplifies porting because you only have to port the language. You do not have to port a user interface, an operating system like thing. The classical distinctions between the language, the environment, and the libraries is maintained deliberately. An important rule in the design of C++, as more features were added, was what we call the zero overhead rule. What you don't use, you don't pay for. C++ has some semi-advanced features, and they can be ever so slightly more expensive to use than the simpler features. But it was very important to us at the time that you should not only be able to write nice programs in C++, you should be able to afford to write nice programs. And for that reason, you should be able to do simple things simply and cheaply. Very important was the concern about real programmers. That is, the language was designed to solve the kind of problems that was facing programmers now, the kind of programmers we had, using the kind of systems they were actually using. It was not a language that was designed to be the greatest language for the interesting problems that programmers might face in the future, and they could handle if they had this wonderful education that people might get in the future, and had available to them the computers that would undoubtedly be available. The focus on being useful now on current users was important and has been essential for the development of C++. Also, I had to remind myself quite often not to try and design the perfect programming language. I must not get involved in a sterile quest for perfection, for the simple reason that people's programs and people's ideals for what is perfect change. And therefore, by the time something is perfect, the world has changed, so it's imperfect relative to that world. Try and do things as well as possible, obey any principle that seems reasonable as far as possible, but we couldn't just stop programming for 5 or 10 years till the perfect language would be available. This led to some restrictions in the design of C++. For example, I decided to use traditional linkers. I really dislike traditional linkers. They were designed to link Fortran 1, Fortran 2, and do that reasonably well. Modern languages are very different, and the use of old DOM linkers is quite constraining. On the other hand, if we didn't use traditional linkers, I would have to provide a new linker for the new systems that we would work on, and I would spend all my time writing linkers. And portability would be difficult, education would be difficult, so stick with old linkers. Another thing was that I did not really want to be in charge of teaching people a complete new programming language. I was relying on C, so that I didn't have to teach yet another way of writing a for loop, say. So the rule of the game was no gratuitous incompatibilities with C. The main example of an incompatibility that is not gratuitous is a violation of the static type system. I systematically remove violations of the static type system, and when I can't totally remove a way of violating the type system, I provide an alternative that does not require a breach. Another technical rule that was useful was that the language should provide the same support for user-defined and built-in types. As a user, it shouldn't matter to you whether the type was invented by Dennis Ritchie when he designed C, or by me when I provided a standard library, or by you when you were writing your application. The rules for scope, for type checking, allocation, deallocation, all of that should be the standard rules of the language. Out of these rules came C++. And I guess the best way of describing C++ fundamentally is to go to an executive summary I once was asked to give of C++. And being a young researcher, I had no idea what an executive summary was. So I asked somebody that was supposed to know, and I got the answer back that an executive summary is something that fits on half a sheet of paper using very large print. And I thought a bit about that and came up with basically a 3-line description of C++. C++ is a better C. It supports data abstraction and it supports object-oriented programming. I guess if you are a high executive, that's sufficient to understand the issue, but I guess I should explain myself a little bit more. C++ is a better C according to rather strict criteria for what better and what C means. First of all, you should be able to do everything in C++ that you can do in C. And you should be able to do it in roughly the same way and with and with the same efficiency. That is, I cannot improve C, making it better, by making it look radically different, by slowing it down, by taking away facilities that I deemed you probably didn't want to use anyway. So that was not it. I can add a few notational conveniences, that's it. The efficiency argument was taken quite serious. For example, we once discovered a systematic overhead of about 3% in C with classes programs compared with C for programs written in the common subset of those two languages. This was deemed unacceptable and the overhead was removed. There is no overhead in a C++ program compared with a C program for a program in the common subset. That's important to a lot of people. The support for data abstraction is where the new stuff begins. This is where the real benefits starts coming. The idea is that instead of just writing a program, you separate the design, the programming technique, the programming process into two parts. First, you design a set of types, set of classes that is meant to map the concept in your application. In other words, if you're an engineer, if you're a mathematician, you may find that the fundamental concepts in your world are things like matrices, complex numbers, triangular matrices, band diagonal matrices, Fourier transforms. And then you say these are the key concepts. You build classes that represent those concepts. And having built this foundation for your application, basically building an extended programming language, extended to suit your needs, you can then write your programs in that language. If, on the other hand, your application area is different, you will use a different set of user-defined types. Say you're doing switching, you'll probably have lines, buffers, trunks, switches as your fundamental types. In a graphics application, you'll have shapes, you'll have circles, rectangles, triangles, smiley faces, what do I know? Languages such as Clue and Ada was designed to support this kind of programming, this kind of approach to programming. It was, however, discovered, even in the early days of Simula, that just being able to do that wasn't quite enough to correctly map the way we thought about things into a programming language. We needed not just to be able to represent concepts directly as types, we wanted to be able to represent relationships between concepts as relationships between types. Let me give what I believe actually to be the original example of this. Somebody wanted to plan the emergency services for a city. The idea is you write a simulator that simulates traffic in a system, and you try and place your emergency services, fire stations, police stations, in such a way that you minimize the time it takes to respond to an emergency. So you simulate the city. It'll have streets and street lights and police stations, fire stations, hospitals. And on the streets are things like cars, police cars, trucks, ambulances, buses, fire engines. And you simulate your traffic patterns, and you see which layout and which kind of dispatch rules will have the fires put out fastest and such. Now, one thing that you notice if you do that, from a data abstraction point of view, is that the code gets rather clumsy. You're coming down the street in some kind of vehicle, and you have to write the code for turning right. And you'll end up writing something like, if you're an ordinary car, turn right the way ordinary cars turn right. If you're a police car, turn right the way police cars turn right. If you're a truck, turn right the way trucks turn right. If you're a fire engine, turn right the way fire engines turn right. And this is necessary because fire engine and truck and police car and ordinary cars are different types, and you have to write different code. On the other hand, it's rather silly because all I wanted to say was turn right the way you want to turn right. And clearly you shouldn't be on the streets unless you knew how to turn your vehicle to the right. On the other hand, they do turn right in different ways. An ordinary car will, at least in a European city, stop for red. A police car will probably go round the corner because it has special rules of the road. A truck takes a rather larger turn, otherwise you'll probably lose something standing on the curb. So what we needed to do was to be able to classify our types the way we classify our concepts and say, well, let's see, buses and trucks and fire engines, well, they're like trucks. Police cars, ambulances, and ordinary cars are like ordinary cars, and they are all vehicles. So you build up hierarchies of types, and then you say, well, it's actually common for all vehicles to be able to turn right, and you should be able to write the code in the vehicle turns right, and have the vehicle turns right in the right way. And the facilities for doing that was built into Simula from the beginning. So it's a very old technique from at least 1967. The work was done in Oslo. I just picked up those ideas. This is usually what's referred to as object-oriented programming. C++'s version of these ideas comes with an emphasis on support for design. I mean, design up front rather than just playing with the code and see how it runs. You can do that too, but the idea is that you do some work up front and provide a design of it. There's an emphasis of static structure and of static checking. The idea being that anything the machine can do for you and anything that can be done early is preferable to leaving things to later or leaving it for people. There was a concern, quite significant concern, about runtime efficiency and of space compactness. This comes from the fact that a lot of the uses that I saw for C with classes and C++ was in areas where time and space was quite critical. Simulations of all kinds of things, not just cities. How about VLSI layout? You may have a couple of million objects in a simulation like that, and you have to find the layout. It is very intensely dependent on both time and space, graphics, and basic systems programming tasks like device drivers, network protocols and such. Clearly, since C classes and C++ were new languages, you had to coexist with existing languages. Otherwise, you couldn't really use the new language till you could do everything in it, and that didn't seem at all sensible. The idea was to fit together with other languages and to fit on existing systems. Throughout the design, I valued experience over theory when there was a clash. Theory is all very well, but it's never a sufficient reason to accept the feature in the language. It seems to me that people are able to argue convincingly for every feature and every technique, and you need a pragmatic approach to stop good ideas spoiling good work. I'm going to talk about the language features provided to support the basic techniques. The first set of techniques I'm going to talk about is how to define user-defined types to fit the needs of a programmer. I'm going to mention three things in that context: classes, abstract classes, and templates. Let me first show how a classical mathematical user-defined type looks like, namely a complex number. The word for user-defined type in C++ is class. The word is borrowed from Simula. I dislike inventing terminology if I don't have to, so since C++ is a direct descendant of Simula in many ways, I use Simula terminology. The class complex is something that you use in mathematical engineering programs. People are used in those fields usually to Fortran, and the C++ code you write has to coexist with Fortran. So we define a complex number to be something that's represented by two double precision floating point numbers called array and m, the real part and the imaginary part of a complex number. That's the representation, and it's private. You can't access it except through operations. To create a complex number, you have to specify either a double or two doubles. If it's two doubles, that of course gives the real and the imaginary part. If there's only one, it's a real part and the imaginary part becomes 0. It comes straight out of a math textbook. The idea in the design of C++ was to provide something that was as close to the application domain as possible, as close to, in this case, the math textbook. So if you have the representation, you can construct complex numbers. All you need is the usual operations like plus and multiply. And then you can look at a piece of user code. And it will look the way user code is supposed to look. You declare a few complex variables, you initialize them either with floating point numbers or pairs of floating point numbers, and then you multiply and add them and multiply with floating point constants, etc. Basically, it's a very constrained exercise. Code written using complex variables has to look the way it's supposed to. In Fortran or in C, it should look just like the integer arithmetic, and that's the way it does. The complex number example demonstrates a couple of important properties about C++ and the way classes can be defined. For instance, hardly any compromise was needed with conventional notation. That is, the code looks the way the code was supposed to look. Somebody acquainted with complex arithmetic can read the code without actually having to know C++ much. I saw an interesting example lately of a piece of C++ code that was immediately readable by somebody who didn't know C++, but knew the area of physics they were dealing with. Whereas I couldn't read it. I only knew C++. I didn't know the right physics. So this mapping, direct mapping, is very important. No compromises is needed in the complex example, and few compromises are needed in general. Furthermore, there's no real compromise in runtime. Code written in C++ in this way will typically run maybe 25% slower than Fortran. It's very, very hard to compete with Fortran, and in this particular case 25% is probably acceptable. You can do better if you absolutely have to. There's ways of tuning the code. A thing that makes this possible is inlining. You do not have to have simple operations such as constructing complex numbers and adding them as real function calls. The compiler can and does inline such things. It's very important that you match something like Fortran or C for layout. That is, it should be possible to pass a data structure, like a complex number or an array of complex numbers, over to a C program or to a Fortran program for processing. Say you have a high-performance machine with special vector hardware, you should be able to take two vectors of these complex numbers in C++, pass them over to a Fortran library, say a BLAS library, and have them processed with maximum efficiency. Such libraries may actually be written in assembly code for a specific machine, and you just can't match that in a higher level language. Similarly, if the data structure hadn't been a complex number, it could have been, say, the time of day structure known to an operating system. The layout compatibility with C becomes essential. If you don't have it, you have to do format conversion whenever you talk to your operating system or your computation library, and that's generally not a very good idea. The space compactness also matters. A complex is represented as two floating point numbers, and the size of a complex number is the sum of the sizes of the two floating point numbers, not the sum of the two floating point numbers plus some housekeeping information. If you have a lot of complex numbers, millions of them, that's important. If you're dealing with a graphics system with a few million points, you don't really want extra overhead in your data structures. The whole issue of efficiency and compatibility, layout compatibility and such, is very important in a transition period. You want to be able to afford to use a new language. You want to be able to compete with older languages, but you want to coexist with them also, because there are things that the new languages doesn't do as well as the old ones, or doesn't yet do as well as the old ones. And even if they did it much better, you still couldn't replace the old code immediately. A gradual transition is very important. Now, this is all very good if you care about old code. And a lot of people at least claim that they don't care about old code. I mean, they want something new and much better. And the usual comment about this is, yeah, but these data types are maybe user-defined, but they're not abstract data types. You don't have a separation between the implementation and the interface. You cannot change the representation of a complex number without having to recompile the whole world, and I don't want to recompile the whole world. Now, my answer to that is twofold. First of all, for things like complex numbers, I am willing to recompile the whole world. As a matter of fact, my complex numbers haven't changed their representation for the last about 12 years. And I'm willing to recompile my world every 12 years. As a matter of fact, I'm usually willing to recompile my world at least once a year. But yes, there are types that change their representation very much more frequently. As a matter of fact, there are types that you want several representations of, and you don't want to bother the user with knowing what the representation is. So let's try to build a truly abstract type. A type is abstract if you can't tell what the representation is. You can only see an interface. And we can define one of those. I'll define a set. And if you look at the definition of class set, you'll see that it has to be abstract because there's no representation specified. And since the representation isn't there, the user can't depend on it in undesirable ways, and we can have alternatives. All we've got in this class set is a set of functions that specify how the set is to behave. There's an insert operation for sticking new elements in. There's a remove operation to take them out again. There's an inquiry operation to see whether something is a member. And just for compactness, I provided a couple of operations for iterating over the members of the set a first and a next operation. Now, if we have such a type, we can go and use it. And a user can use it using only the interface specified, and the code will look sort of fairly conventional. The function my takes a set as its argument, and it iterates through it, presumably doing something with all of the elements. All the user can do for iteration is to ask for the first element and then carry on getting the next element till you run out. And it's a perfectly conventional C4 statement. And we use only the abstract type. The interface is visible to users. That's all the users know. It's all the users can use. Now, of course, somebody has to know what the representation is. You cannot create a set without saying something about what kind of set it's supposed to be. You have to say not just that it's a set, but what its representation is. So somebody can use my code by giving it a couple of sets. And the example here is somebody making an S-list set and a vector set, and presumably those are kinds of sets implemented with single linked lists and arrays. And you can pass that to my code. This is fine. My code gets an S-list set, my code gets a vector set, and it works correctly. As a matter of fact, when I wrote that code, I had no idea what sets there really were. The user creating those sets, of course, has to have access to the definition of S-list set and vector set, but doesn't really have to worry too much about what they are. On the other hand, somebody has to define the sets. And if you look at a definition here, we have an example how to define an S-list set. An S-list set is a set that is a set, that's its interface, and it's implemented. We can see from the definition of S-list sets that it's implemented using an S-list set and it has a current element. That's the representation. But what's really important is that it defines all the operations that's required by a set. An abstract class like set specifies that certain functions must be provided, and in this case they are. If you forget to define one of them, the compiler will catch you and will ensure that you do not create objects of a type that doesn't actually provide the functions that its interface says it provides. So the set example shows how you can separate the interface from the implementation. And it also showed how you typically use a data type that doesn't have that kind of separation in the implementation part. So you can use the other kind of classes, the ones where efficiency and compactness matters, to implement the ones where separation matters. There's just one thing that sort of is slightly unrealistic here. You don't actually want a set of t's the way I defined it, at least not unless t happens to be one of your favorite data types. You want sets of, say, complex numbers, sets of pointers to shapes, sets of some data types I've never heard of, because you're only going to define it tomorrow. In other words, you want t in the set example to be a parameter that you can specify so that you can make sets of different kinds. I wrote an example of how that's done. I used a stack instead of a set. It's a perfectly ordinary stack. It's written in terms of stacks of something called, of an element type called t, and then I've just prefixed the stack declaration with the prefix template class t, and that says it's a stack template, and that that t is a parameter. Then you can make individual classes from this template, like stack of integer, stack of complex, stack of shape star, and the language will ensure two things. First of all, it will ensure that the classes, specific classes like stack of integer, behaves the way a stack of integer should according to the definition of the stack template. Furthermore, it will also make sure that that class will be generated in a proper way. Let me give an example of how this works out. I will take a stack of pointers to planes, and it is a language job to make code work provided you use it only in the appropriate way for stacks of planes. And I have promptly started to misuse it by pushing a Saab 900 and a Saab 37B on it. Now, a Saab 900, if it's at all reasonably defined, is not going to be a plane. Saab 900 is a car. So the rules of the language ensures that you can't push it on a stack of planes. The Saab 37B, however, is all right because the 37B is a reconnaissance plane. So when I try to write the code pushing the 900 on the stack, it will not work. I'll get a compile time error. This contrasts to the use of dynamic type checking in some languages like the Lisp variant and Smalltalk, where you simply say, I want a stack of anything you like, and I can push anything on the stack. So here it would work to push a stack 900 on and a push a 37B on. That is fine. You will catch the error later when you try to misuse the object, like when you pop the stack and ask the last thing to be pushed on to take off. That'll work fine because the last thing to push on was a Saab 37B. That's a plane. If you try and do it again, popping off the Saab 900, things are not going to go so well. A 900 is fast, but it's not going to stay in the air. So you get a runtime error, and you presumably find yourself in a very nice debugger. Now, this is fine. If I'm debugging my code, finding the error during debugging is not, in my opinion, as good as having a compiler find it before debugging, but it's sort of acceptable. On the other hand, if you were debugging your code and it was some of my code that generated the error, you may be less tolerant. And if you are an application user and not a programmer, you could get quite annoyed. So you have a trade-off where you find your errors, and consistently the design decisions in C++ has gone towards finding the errors early using static type checking. Basically, the classes and the abstract classes and the templates supports the data abstraction notion. That is the ability to take some kind of concept and represent it in the code as a type. What we need to do to get to object-oriented programming is to be able to represent class hierarchies, represent relationships between different types. And I'll show two ways of using that in C++. The first one is building up types in stages and then taking advantage of the way they were built up. For instance, you can have a class shape, and a shape has a few properties, like shapes has a center and shapes can be rotated and drawn. But basically you can't give more properties than that to a basic shape. Like, you don't actually know how to draw a shape in general, because general shapes can't be drawn. You can only draw particular shapes. So the draw and rotate functions are defined to be virtual, to be defined later when we know what to do. So We can then define a circle, and a circle is the kind of shape that has a radius and that you draw in the way you happen to draw circles and rotate in the obvious way, that is doing nothing. And you can then build again on that. You can build a smiley. A smiley is the kind of circle that has two eyes, that have two eyes and a mouth. And once you've defined this hierarchy of classes, you can start using it in code. A piece of library code might be written simply in terms of shapes. And I have a library, sort of imaginary library piece of code called rotate that takes a set of shapes and rotate them a number of degrees. We use the properties of the abstract class set so that we can iterate through the set, independently, of course, of what kind of set we are dealing with. This set could be an S-list set, it could be a vector set, could be a kind of set that I'd never heard of when I wrote the library code, doesn't matter. And then each of the shapes it gets, we ask to rotate the right number of degrees. And well, again, we don't have to know what kind of shape it is. The shape coming in could be a circle, it could be a smiley, it could be a town map of Manhattan. I don't know. A user can create a particular kind of set, fill it up with shapes, and pass it to the library code. And this will work even if the library code is compiled before the particular kind of set has been invented and before the particular kind of shapes that are put on in the set has actually been defined. Those are important degrees of freedom for a library designer, and the thing it relies on is that both shapes and sets conforms to the interfaces we have specified for them. This is the basic way of using C++ class hierarchies. Sometimes it's not quite enough. When we come to using libraries, and when we have large software systems composed of classes and defined by different people at different times, sometimes we hand an object of a type we know over to somebody else, and then we get it back again later. And we may pass a smiley over to a graphic system and may be given back to us. But since the graphic system will be written in terms of the basic abstractions available in graphics, like shapes, and know nothing about my little shapes that I happen to like smileys, when it is passed back to me, the exact type has been lost. And sometimes I just have to be able to ask, now, is the shape that came back to me really one of mine? And that is done by something called runtime type inquiry. Here's an example of a dynamic cast where I get a shape back. I ask if it's a smiley. If it is a smiley, I get back a pointer to the smiley. If it's not a smiley, I get back a 0, and therefore I can test. If it was a smiley, I do what is appropriate for smileys. If it's not, I must do something else. This becomes quite significant when you're dealing with the event-driven systems and if you're dealing with large standard libraries. If you think smileys is a slightly frivolous example, think of it as a dialog box or an event that has been triggered, one of many events that the system might respond to. In a real sense, classes and derived classes, class hierarchies, runtime type identification, supports the writing of large software systems. There are also facilities in C++ that has come in over the years as the systems built in C++ has grown, and they are specifically designed to be supportive to users of large systems, writers of large systems. I'll describe here namespaces and exceptions. Now, the problem with namespaces is that people who write code will use a few names. And if you have lots of people writing code, they will, by accident, use the same names for different things. Like everybody will have functions called draw and open, plus and such. They will define classes called strings or complex, something like that. And somehow or other, we have to make sure that the names and the things I name doesn't collide with the names you use for the things you need. And the basic mechanism we have is called a namespace. I put my names into my namespace, and you put your names into your namespace, and the net effect is that the two does not clash, even if a third person uses your code and my code. The only problem remaining is that we have to be sure that the user can use our names also. And the basic way of doing that is simply to say whose names they want to use. Like if I want to use a string, I say a : string. That's pretty obvious. And if I want to use B's function f, I use B : f. If that gets tedious, you can say that, well, I want to use names from namespace B, and that means if I use a plain name like string, it will be B string. Conversely, you could say, well, I would just want A's f also, and that means if I use f, it is A's f. Fairly simple mechanism. It's all compile and link time, but it overcomes a rather serious problem encountered in languages that doesn't have it, notably C and C++ in earlier versions. Now, this allows us to write code that is separately developed, merged together without name clashes. It allows us, with the classes and the derived classes, it allows us to represent concepts directly. The only problem is that when you start writing code this way, some errors remain to be caught at runtime. And the problem becomes of how to report and how to handle the errors that are caught. A library can, of course, catch errors that occur at runtime. Like if you have an array class in a library, that array class can detect an out-of-range access. That's easy enough. On the other hand, it doesn't know what to do when you get an out-of-range error. Only the user knows what should happen. I mean, maybe it's critical that there is an out-of-range error. Maybe it's not. If it was simply a data gathering piece of code and you are trying to write outside the edge of an array, it simply should be ignored. That's quite acceptable in some cases, but you certainly shouldn't start scribbling in the wrong part of memory. So libraries can detect errors and users can specify what should happen when errors occur. It's a difference between a mechanism and a policy. So we have the situation that a user can say, if I goof, do X, and the library can say that you goofed. The real snag is that there's many ways of solving this problem. We have things like return values. We have state variables that could be set. There could be error functions to be called. Every library that's ever been written has something like that. The snag is that most two different libraries usually uses a different kind of strategy, and if somebody uses several libraries and have to deal with several different error strategies, the code becomes unmanageable. We need a fairly standard way of dealing with errors detected at runtime, and that mechanism is known as exceptions. The way you write it is that you write something called a try block, and any code executing in the try block or called from the try block, you can check whether certain kind of errors, unusual circumstances, exceptions happen. In this case here, I say that if an I/O error happens, I want to know about it. So if an I/O error happens in the code, in the try block or dynamically below, I will find myself in the handler catch I/O error, it's called. So we go and execute the code, and we may get down to this function h that does some I/O. It checks whether things are all right and finds that an I/O buffer is overflowing, and it throws the specific I/O error buffer overflow. Now, this error this exception propagate up to the catch block, and it notices that a buffer overflow is defined to be a kind of I/O error, and we catch it. So there's two things that are important about this code. First of all, we can catch I/O errors. Secondly, we do not have to know the details of I/O errors. We'll catch any I/O error, whatever it's called. Basically, we are using the class hierarchies, the derived classes, to express the grouping of different kinds of errors. And that's an important degree of flexibility in the way you deal with errors. So much for language features and programming techniques. A question I'm asked quite often is how and why and where did C++ get used? Why did it grow? First of all, it grew without the use of advertising and marketing in the traditional sense. As a matter of fact, for the first 3 years, the advertising budget for C++ from AT&T was $5,000. We wasted $1,000 on a letter to system administrators. Nobody read that. The next $3,000 was used on a reception at the first C++ conference. That didn't help C++ either, but we had a nice party. And the rest we had to give back. We couldn't find a good use for it. On the other hand, not having major overhead meant that the price was tended to be right, and we tended to encourage self-sufficiency among users. That was very important. We also had a strong emphasis on portability. The average time to port to a new system for somebody who didn't know C++ was about a week. The record was about 3 hours for somebody who was moving to a completely new system without knowing C++. C++ was powerful and expressive compared with traditional languages like C and Pascal, and it was fast and compact and cheap compared with everything that had abstraction mechanisms that put it in the league with C++. The growth of C++ was always worldwide at users basically everywhere, but the emphasis was in the US technology-oriented industry, but there was always a strong use in various sectors of industry and in academia. Basically, I guess the reason C++ was a success is that it's a very practical general-purpose programming language with an emphasis and a strength in systems programming. You can do various kinds of programming in C++, traditional C-like programming, data abstraction techniques, and object-oriented programming, but nobody is forcing you to do it, and you can do it in in a variety of environments. Basically, C++ succeeded because it addressed real needs to real users. And it certainly did grow. I tended to try and count C++ users, and at the end of 1991 I stopped because I couldn't count users anymore, and at that point there was about 400,000 C++ users. It's very hard to get hard figures there, but I know that the most popular C++ implementation has sold 1 million copies. So it's rather large numbers that we are dealing with. With lots of implementations and lots of users, we need some kind of standards effort, and that was started in late '89, and by ANSI, the American National Standards Organization, and ISO, the International Standards Organization, joined in 1991. The initiative was taken by IBM, DEC, and HP, basically to avoid chaos erupting and to make sure that the language were under standardization. This created a forum for debate and for dissemination of ideas that's very important to stabilize the language and to make sure that the language is responsive to wider needs, and importantly make sure that no single company exerts undue influence on the language. Clearly, standardization is not easy. People have to agree, and it's especially difficult because the language is still evolving. There were people that considered standardization of C++ at the time premature because major features such as exception handling and templates were new at the time. But we hope to get a standard soon, and the draft standard is June-September 1994. The main challenge has been to maintain the coherent language, and I think we've succeeded so far. There are no features in C++ that I don't think ought to be there, and I do not miss any major features in the language for the kind of uses I consider. The challenges in the future is primarily education. That is, you can do a lot with libraries, you can do a lot with tools and with design techniques and environments, but fundamentally the main challenge is for programmers and designers to learn how to use the tools we've got well and design and implement the systems using the facilities that we've got. C++ has some real strength in low-level systems programming and also in higher-level systems programming, and its use is getting into general application building and also into numeric scientific engineering applications. The greatest strength is probably in systems that has a combination of everything. If you have a system that has to do a bit of database work on a mainframe, you have to do a bit of networking, you have to run some gadget like a stock trader's trading pad, you have to do some visualization on a mini supercomputer. Few languages can do all of those, and C++'s greatest strength is I think, in areas where you have a mixture of challenges, a mixture of application areas. Well, basically I think C++ is still very young. It's a young language, and we've hardly begun to see the benefits that we'll get from its use. Thank you.